So the topic of our today's talk would be higher topological quantum field theories. The title sounds frightening, but you will see that it's kind of a simple concept. And I will write it with the simplest example. That is higher topological quantum mechanics. With simplest examples, with the simplest example. So let me remind you that our main object was a functor. From category of geometrically enhanced or enriched cobordisms to category of vector spaces. In particular, this is a cobordism, and the value of the functor on this cobordism was belonging to endomorphisms. Sorry, not to endomorphisms. Homomorphisms. V in, V out times functions on geom. So this is geometrical enhancement. And there was the main equation for this to be a functor. F applied here is F of this one, composition with F of this one.
I'm sorry, shouldn't the geometrical enhancement be on the on the other side under the functor in some way?
You see, it is a dual side. It's a good question. It's a dual question. When I say that F belongs to functions, it means that for each geometry.
Okay.
G1, I can consider evaluation of the functor at point G1. And this belongs to homomorphism. And this is evaluation. And the simplest example is just one-dimensional cobordism, smooth. where geometrical enhancement just metric. So f of this interval with metric G1, G2 is f of this interval with G1 composition with f G2. So this is functoriality. In particular, if we assume invariance with respect to diffeomorphisms of the cobordism, then G1 moduli diffeomorphisms is what? Length of the interval. So we will get f T1 plus T2 equals f of T1 so f of t is just exponential map. And we call it Hamiltonian. Now we go from mathematics to super mathematics. So in particular, it goes from, here we go from manifolds to Q super manifolds. So we go from vector spaces to complexes. So we go from functions on geom to differential forms on geom. And this is exactly two functions of t shifted by one geo. Moreover, functions of t1 on geom may be considered as a Q manifold with a homological vector field de Rham differential. In this sense, T1 geom as a manifold together with D de Rham is a model of the new manifold called top. I will say honestly, So from the modern point of view, the functor takes values in homomorphisms of V in, V out, and here functions here. So differential forms on geom. Moreover, from the modern point of view, V in, V out should be considered as complexes. So when I write this differential Q, I somehow assume that I'm a mathematical physicist. Mathematicians never call it Q. But it is only the name. The concept is the same. So now I'll say that I will impose extra axiom. You see, each axiom is very important. Axioms in fundamental concept are very, very important. I cannot just invent them like this. It is a very important step. You see, since it's an important step, I'll just put it like this. So higher topological quantum field theory is a closed functor. From geometrically enriched cobordisms to complexes of vector space. Let me underline what changed. So main object belongs to and B plus Q applied to F equal to 0. And this is the closeness axiom. I just want to say that the closeness axiom looks extremely natural from the supermathematics point of view. But we will see that it is also natural from the point of view of higher mathematics. Where we take into account homotypies. We just not throw them away. We trace them. So mathematicians would like it, and physicists would like it, and we will see examples of it. So this was abstract blah, blah, blah. You see, abstract blah, blah, blah is nothing if you don't have examples. Sensible mathematics is when you have abstract plus interesting examples. It means that abstract blah, blah, blah somehow generalize your interesting examples, and you create a new world of structures. Nobody is interested in abstract blah, blah, blah without examples. Consider simplest example. Quantum mechanics. I'm sorry. So now the main object, F, is an operator that depends on T and dt. Here I move from functions on the length to differential forms. And I have a functoriality. And closeness. So people say that it should be not called closeness, it should be called closedness. Closed. You see, however, for me to write closedness is too hard to pronounce. But probably it is a proper word.
Closeness means more like being near.
Yes, that's why native speaker told me that closeness is not a proper word. So it's closedness. Okay. So I will pronounce it as closedness. Okay. It's my common mistake. Closedness. Okay.
I have a question. So if our functions are on this t shifted by one of geometrical data, and here is just it's just the differential forms are of the form dt, then what does q do? Where does it act?
Okay. U is a differential in V. In the functor, we associate to this V that is a complex. And we already mentioned it here.
Okay.
And in order to distinguish these two things, I will call one differential D and another Q. So it's super mathematics. So the question would be how to solve it. Let me give you a solution. So it's an exponential of what? Of D plus Q, anti-commutator, applied to GT. Where G is a map from V to V, G is odd, and I will also demand G squared to be equal to 0. And here I have multiplication. So here I have, okay, so it depends how okay, so here I have first term, HT, so I like it. Sorry, the brackets are round brackets. So the first term comes when I anti-commute here, and I write it, H is an anti-commutator of Q and G. However, I have a second term, where this D. To show that this D is related to geometrical data, I put T here. And I put T here. And here I have, so this anti-commutator gives me minus G dt. And this is exponential. Here I can easily write dh. And here I expand the exponential. And I write it as 1 minus G dt.
But this is assuming that H and G commute.
Exactly, that's what I'm trying to write down. Here I use that H and G commute. Really, commutator of G with anti-commutator with this is 0 due to G square equals to 0. Thus, topological quantum mechanics is given by a pair.
What is the commutator between H and G?
0.
G is odd, H is even.
So here is the commutator between H and G. So it's a basic thing. So maybe I would not run here. Okay.
That form of the answer, is it obvious? Like how can we
How can
how
we?
can we arrive
Okay.
at this?
Okay. How did I get? For any differential d e to the d of something of r equals to 0. It's a lemma. So probably I should write it like this. Commutator.
But that is true for quite a few functions, right? Like I can put any function instead of e, and that would also work.
Okay. So interestingly enough, so this is for closeness. But I also need functoriality, closedness. So 2 axioms is not 1 axiom. And functoriality means that I would like to get some kind of exponential. So let me explain lemma. So first I will say some words from high mathematics, then confirm it by computation. Okay? On conceptual level, in homotopical algebra, there are no signs like equality. The only no operations, no symbols. The only symbol is equivalence. You see, since I'm teaching you concepts, this comes from the John bias. Slogan. You see? A equals B is either trivial or wrong. If A is B, it is trivial. If A is not B, it is wrong. So instead, we need to say that A so this is the only reasonable formula in mathematics. It says, it reads, A is equivalent to B in equivalence relation gamma. So it is very deep. It should be taught at school. But this is called homotopical view. On mathematics. However, there is a science called algebraic topology. In the science, we turn homotopical considerations into some kind of an algebra. It means, first, we formally may add and subtract objects. It means that we are take their formal linear combination. We understand A homotopically equivalent to B as A minus B is D applied to some C. Example. Two points on the manifold. That belong to the same connected component. May be connected by a path gamma. Point is a figure. Path is also a figure. And we write it as B minus A and this is the boundary operation. Continuation of example. It could be that gamma 1 may be deformed. Into gamma 2. So there is sigma such that the boundary of sigma is gamma 2 minus gamma 1. In particular, d square of sigma is d gamma 2 minus d gamma 1, and this is, so how do they call it, b minus a, and this is 0. Follows from the universal principle d square equals to 0. In this case, we say that two homotopies are equivalent It may happen. Consider torus. Consider 2 points A and B. And this is gamma 1. Or not homotopical. With each other. So if you start thinking about this, you will build algebraic topology. Means belong to cohomology of this operator. In the space of one cycle, etc. So actually what I gave you here is a brief introduction to algebraic topology. Now back to conceptual understanding of the formula. Sorry. ER is homotopical 0. Okay? E to dr is homotopical e to the 0. That is 1. So e to dr and of course D of 1 is 0. Okay? So this is a conceptual way to understand. Now algebraic proof. Plus etc. Now here we clearly have 0. It follows from d square equals to 0. But may be pronounced as d of homotopical 0 is 0. Now we have this. And here I use Leibniz rule. But this is 0. Okay, I guess I forgot something. But this is 0. And this is 0. So altogether it's 0. And so on. Lemma is proved. Okay? So now let us have a bird view. I prove this lemma. Okay? Tim?
Well, yes, but I have another question. So, what if we replace this odd element R with something even? Why can't we do that? It looks like all the properties will still be satisfied, but it will be just a E of the commutator of D with some, I don't know, B. We don't do it because
So you may ask why R is why we consider R as odd.
yes.
So it's a good question.
I understand that then the thing in the exponent is even, and the whole operator e to the power is even. That is nice, I guess, but why do we need this restriction?
Okay, so here it's a question that I have not solved. Question of team. Are there other solutions to a system? So I actually don't know, to be honest. I proposed the solution. So in all examples that I have met, it was enough. But maybe there are other examples. So I need to be honest, I never studied this system, TQM, in full generality. Let me consider examples of, say, my solution. Example number 1. Consider a manifold X. Take V to be differential forms on X. Take U to be D on X. So I decided to put this X on the top. Take G to be, sorry, it's better to put it on the bottom. You will see why. Sorry. what I'm writing. Equip X with a metric G. Take G to be Hodge dual. Then H is Laplacian on X. It's a good example. Example 2. Again, consider and V to be omega dot of X and Q to be dx. But now equip with a vector field. And take G to be contraction. So for people who don't know what contraction is, I would say if omega on X are just on X mu psi mu, then EV is the following operator. Then H is anticommutator of dx iota v. And this thing is known as Cartan formula. So my goal is not just to provide you with a variety of examples. We need to have to make a moral of example 1. Theory considered as physical with Hamiltonian equal to Laplacian is a subsector of higher topological quantum mechanics. What does it mean? It means that if I restrict myself to subsector V naught inside V of differential forms of degree 0, I have a physical system. Describing a free particle moving on X. But then the question may be, okay, well, it works. For a free particle. What about potential? And it turns out that it is possible to do it with a potential too. So to do it, I would like to change Q. Let me conjugate d by e to the w. You may not know what w is, where w is just some function on X. So what does it mean? I'll write QW given by the following formula. Clearly, dW square equal to 0. By the way, dW is known as Witten's differential. Interestingly enough, W was a standard notation for so-called superpotential. Had no relation to Witten. Now, Q is dW, and let me take G, dW star star. So, Hamiltonian W would be equal to dW star dW star anti-commutator. So let us compute it. It is definitely a Laplacian plus Okay, plus or minus Laplacian. And here we will have dw anti-commutator with star dw star. What does this thing mean? Plus terms linear in W. So dw is actually dw over dxi psi I. Now star dw star is the following: dw over dx j d over d psi I gij. So this is the metric on x. So together dw star anti-commutator and they see contribution only from psi's and d over d psi. Okay, so I already see minus Laplacian plus potential. However, I have two extra terms. So this is d, and here is dw. What will this mean? Sorry. And here I have the following term. So first term is like this. plus I will have a commutator from here. Similarly, I will get a term from d star d d double. What would this be? And once again, I will get the term plus the first derivative term. So altogether, I have a potential that looks as plus something like psi d psi w2 prime and plus probably now what can I say? Now Laplacian W is clearly Hermitian. So if it's clearly Hermitian, it cannot involve terms like they are anti-Hermitian. So they have to cancel. So potential is dW. We will put it like this, plus second derivative of dW and psi d psi term. Once again, if we restrict to omega 0 of x, it will say no dependence on psi, we will get a potential. So we have moreover Hamiltonian W preserves omega naught. So we have a quantum mechanics with potential U as a subsystem. Why don't work? Of higher topological quantum mechanics. And this is kind of a remarkable fact. Says that higher topological quantum mechanics are not that topological. They have physical systems as their subsystems. And then there is a conjecture wild conjecture. Could it always be like this? Yeah. Quantum field theories are subsystems of some higher topological quantum field theories. If it is true, then instead of studying quantum field theories, we should study higher topological quantum field theories. Interestingly, for quantum mechanics, it is always true. And it's very interesting theory. that I'll explain right now. Suppose we have a quantum mechanics with space of states that is image of a point of boundary point due to functor. F of point is V. Consider a new quantum mechanics that would turn out to be a higher topological. It would contain space of states HT. That is C squared times V. Quantum mechanics had a Hamiltonian. Now we will write Q it is a block representation. Due to structure. And we will write G as follows. Then QG would be so on states of the form V0 Q of G equals H with embedding. Okay?
How do I see that Q and G in this point are Grassmann odd?
Ah, good point. Good point, because it means that I need to write here not C square, but C1/1. So it means that when I write element like this, V1, 0 are even, are odd. Operators that map even to odd and odd to even are odd. You see, Q and G are off diagonal, so that's why they are odd.
Yes, they are off diagonal, but it's just the Z2 graded.
Yes, it is just Z2 graded.
You do not mean by Grossman odd.
It's the same. But since you are asking it, I will write equivalent form. Consider an odd number, C. I call it C due to historical reasons. I will call it C. Then V higher topological quantum mechanics would be while this space is a span of 1 and C. Okay? Okay, so it means that I wrote it not at the proper place. Now I can rewrite U as CH. And I write G as D over DC. Now it is clear that Q is odd because it contains C, and G is odd because it contains derivative. Moreover, QG is CH T over DC. So this is just H. For future, in dimension 2, when we will study conformal quantum field theories, I am not explaining it right now. It is for future. So how do I understand G that was d over dc. I consider the integral b dc over dt. And I consider this integral, and I fix c at 0 is c naught, c of t is c1, and I understand it as k c1 c naught. Then b would be d over dc naught, just like in the example that we studied before. Where p corresponded to d over dx. Okay? So I keep it for future. So you should know that the simplest examples that I am considering are not just because these examples are simple. It is because that they have multi-dimensional generalization. Because our goal is not to study topological quantum mechanics, higher topological quantum mechanics. Our goal is to understand something about quantum field theory. And in particular, we see that surprisingly, quantum field theory probably could be embedded into topological quantum field theory. Higher, of course. And we studied the case of quantum mechanics in some detail. Okay, so that's it. That's what I wanted to tell you today. And I will continue with examples tomorrow. Okay? But I introduced one important concept. It's a concept of higher topological quantum field theory and higher topological quantum mechanics. And they provided it with examples. I just want to say that the G operator is nothing but homotopy for H. One second. I write it all the time. And I want to box it. G is homotopy for H. H is homotopically trivial. But here we are keeping homotopies. We are not forgetting homotopies. We are keeping homotopy. And H in higher topological quantum mechanics is homotopically zero, but only homotopically zero. G says how homotopically zero it is.
Do you mean cohomology? Not
I mean homotopy. Homotopy is something that vanishes in cohomology. So there are two things. There is a thing called homotopy, and there is a thing called cohomology. You see, I don't know how much of homotopical language do you know. I just try to explain something. Here, this is a homotopical language. In this example, points A and B are equal in homology. And this is because their difference is exact in the space of figures. So difference A and B is 0 in homology. But sometimes it's important to keep homotopy. So keeping homotopy means that we are not throwing away gamma. We are keeping this gamma. Let me draw you a picture. Suppose we have X. Suppose we have this C. Homology of this C is 0. Okay? Because this C is contractible. Because this C is actually the boundary of sigma. In primitive theory, we just say, let us throw away all boundaries. However, in higher theory, we trace all homotopies. We are not saying that C is 0. We rather say that C is the boundary of sigma. H is not 0. H is Q of G. Okay? That's why I call it higher. Higher means that you are not forgetting homotopy, that you are remembering them. Okay? So when people started doing homotopical algebra, they started with saying, let us put all homotopies to 0. But it was the starting point. Then people realized that it is very important to keep homotopies. Let me give you an example from enumerative geometry. This is called linking of two cycles. It is clear that you cannot take away C1 and C2 without crossing C1 by C2. Linking is the following. Consider C1 as a boundary of sigma 1. then linking C1 and C2 is sigma 1 intersected by C2. So if you would like to understand the linking, and in more general case, knots, maybe you heard about knots. You need to remember how C1 is contracted to a point. It's just an example. So if you would like to see linkings, you are keeping information about this sigma 1. And it is also the subject of numerative geometry, linking. So it's not just homology. So we will come back to this issue tomorrow. So I will continue writing you formulas in two ways. In geometrical way, like here, and in algebraic way, like here. So H, so people from homological algebra would say, look, H is somehow contractible, and its homotopy is G. I hear people say that C1 is contractible, and its homotopy is sigma 1. However, you can play with contractible C1s and get interesting things. In numerative geometry, you have a linking. In algebraic context, you have higher topological figure.